Welcome all. Now we are going to discuss Theorem 9.3. This theorem has two statements, and the first one is called resonance theorem. The statement is, let X be a normed space and capital E be a subset of X. Then E is bounded in capital X if and only if f of E is bounded in K for every f element of X dash. And the second statement is, let X and Y be normed spaces and f from X to Y be linear. Then f is continuous if and only if G composite f is continuous for every G element of Y dash. Okay, so first we will look at the proof of the resonance theorem. For this we have capital X be a normed space and E be a subset of X. So we are proving that if E is bounded in X, then f of E is bounded in K, and conversely if f of E is bounded in K, then E is bounded in X. So first we assume E is bounded in capital X. This means that norm X is less than or equal to alpha for every X element of E for some alpha positive, right? Now choose f element of X dash, then consider mode of f of X. This is less than or equal to norm f into norm X clearly, because f is an element of X dash, and so this is less than or equal to norm f into alpha, because we are for every X element of E, because we have seen that E is bounded in X, so norm X is less than or equal to alpha for every X element of E. So this means that modulus of f of X is less than or equal to norm f into alpha for every X element of capital E. This means that f of capital E is bounded in K for every f element of X dash. Because for f element of X dash, norm f is a constant and alpha is also again a constant, and so modulus of f of X is less than or equal to norm f into alpha means which is less than or equal to a constant actually. So this has happened for every X element of E. So f of capital E is bounded in K for every f element of X dash. Okay, this is the necessary part of the resonance theorem. Now we have to prove the converse part. Conversely, assume that f of capital E is bounded in K for every f element of X dash. Now we have to prove that E is bounded in X. For that we are considering the canonical embedding J from capital X to X double dash, defined by J of X is equal to Jx. That is, J of X of f is equal to Jx of f, which is equal to f of X for every f element of X dash and for all X element of X. Okay, then since norm of J of X of f, which is equal to modulus of f of X, which is less than or equal to norm f into norm X for every X element of X and f element of X dash, this means that J of X is bounded. J of X is a bounded linear map, right? Because because norm of J of X into f is less than or equal to norm f into norm X, means norm of J of X into f is less than or equal to norm X into norm f, right? For every X element of X and for every f element of X dash. So by theorem 6.2 we can say that the map J of X is a bounded linear map, that is J of X is continuous. Okay, so J of X is an element of BL of X dash K for every X element of X. That means if this happens for every X element of X, then it is clear for every X element of E, since E is a subset of capital X. That is, J of X is an element of BL of X dash K for every X element of capital E. That is, the set of all J of X where X element of E is a subset of BL of X dash K. Also we know that X dash is a Banach space, because if X is a normed space, then X dash is clearly Banach. Okay. And also for each f element of X dash, the set of all mod J of X of f where X element of E is equal to the set of all mod f of x because j of x of f is equal to f of x. So that is equal to set of all mod f of x where x element of e is bounded, because we are assumed that f of e is bounded in K for every f element of x dash. So modulus of f of x where x element of e is bounded by our assumption. That is set of all mod j of x of f where x element of e is bounded. So supremum is clearly less than infinity by 9.1, theorem 9.1, uniform boundedness principle. Because for applying the uniform boundedness principle, here we have the Banach space capital X dash and normed space K, and considering BL of x dash K, we have a family of members j of x where x element of e, such that modulus of set of all modulus of j of x of f where x element of e is bounded, that is pointwise bounded on e. The family j of x is pointwise bounded on e. So we are at a stage of applying the uniform boundedness principle, and using that we can say that supremum of all norm of these family members, that is supremum of all norm of j of x where x element of e is clearly less than infinity, using the boundedness uniform boundedness principle. Okay, this means that the set of all norm j of x where x element of e is bounded. Since the supremum is finite, we can say that the set is bounded, but norm j of x is actually equal to norm x. How? Norm j of x is by the definition, that is equal to supremum of all norm of j of x of f where f element of x dash with norm f is less than or equal to 1, that is equal to supremum of all mod f of x where f element of x dash with norm f less than or equal to 1, and this is by definition this is equal to norm x by the theorem 7.10 a part. This is nothing but equal to norm x. So we have a set of all norm j of x where x element of e is bounded, that becomes set of all norm x where x element of e is bounded. This means that e is bounded in capital X. Okay, so we have proven the converse part, that is if f of e is bounded for every f element of x dash, then e is bounded in capital X. Okay, this is the proof of resonance theorem. Now we will discuss the second part of this theorem. For that we have x and y are normal spaces and f from x to y a linear map. We have to prove that if f is continuous, then G composite f is continuous for every G element of y dash, and conversely if G composite f is continuous for every G element of y dash, then f is continuous. Okay, suppose f is continuous first, then we have to prove that if G element of y dash, then G composite f is continuous. Okay, so choose G element of y dash. This means that G is continuous, and by our supposition f is also continuous. So we can say that G composite f is continuous because composition of continuous functions are continuous. So we have obtained that G composite f is continuous for every G element of y dash whenever f is continuous. Now for the converse part, suppose G composite f is continuous for every G element of y dash. Now we have to show that f is continuous. For that, let capital E equal to the set of all capital F of x where x element of x with norm x less than or equal to 1. Then clearly E is a subset of capital Y because f is a map from capital X to Y. So f of x is clearly is an element of capital Y. So clearly capital E is a subset of capital Y. Also G of capital E is equal to G of capital F of x where x element of x with norm x less than or equal to 1. That is equal to set of all G composite f of x where x element of x with norm x less than or equal to 1. that is equal to G composite F of Ux closure of 0, 1, which is the closed ball with center 0 and radius 1 in capital X. Okay, because x element of x with norm x less than or equal to 1 is simply Ux closure of 0, 1, right? So this means that G of E is equal to G composite F of Ux closure. Okay, but we know that Ux closure is closed in capital X, and G composite F is a function from capital X to K. Okay, that is G composite F, actually G is from Y dash, that means G is from Y to K and F is from X to Y. So G composite F is a map from capital X to K, and it is continuous by our assumption, because we are assumed that G composite F is continuous for every G element of Y dash. So by our assumption, G composite F is an element of X dash. Okay, and G composite F of Ux closure is bounded in K, because Ux closure is bounded in capital X, and by using the resonance theorem, we can say that G composite F of Ux closure is bounded in K, because Ux closure is bounded and G composite F is continuous. So by resonance theorem, G composite F of Ux closure is bounded in K. Okay, that is G of E is bounded in K for every G element of Y dash, because G of E is equal to G composite F of G composite F of Ux closure. So G of E is bounded in K for every G element of Y dash. This means that E is bounded in Y by again the resonance theorem. Okay. For applying that resonance theorem, we have G of E is bounded in K for every G element of Y dash, means using that theorem we can say that E is bounded in capital Y clearly. So this means that set of all norm f of x where x element of x with norm x less than or equal to 1 is bounded, because this is the definition of capital E actually. So E is bounded in Y means norm of that elements in E is bounded. Okay, this means that the function capital F is bounded on Ux closure of 0, 1. Clearly this is because we have x element of x with norm x less than or equal to 1, that is we have chosen the elements of Ux closure of 0, 1. So set of all norm f of x where x element of x with norm x less than or equal to 1 means the norm of that elements, that is capital F is bounded on Ux closure of 0, 1. Okay, this means that F is continuous by theorem 6.2. So we have proven that if G composite F is continuous for every G element of Y dash, then F is continuous. Okay, this is the proof. Thank you.